We often dream of a future out in the galaxy, exploring and settling strange new worlds under the light of alien suns. But what would living in space truly be like? Last week we were talking about near-term space colonization and some of the hurdles we would encounter on our journey to settle new worlds. But we didn't talk much about what living in space itself would actually be like and what the challenges for humans are when living off Earth. It's a big topic because space is big, really big. You just won't believe how vastly, hugely, mind-bogglingly big it is. And that also means that there are a lot of different conditions humans would need to adapt to in order to live in those places, or adapt them to our needs, or possibly meet somewhere in the middle, as we often have in our history on just this single world and its many different climates and ecosystems, which again is but one world among billions and billions. Now, we're not talking today about living in the actual void of space, which is empty of everything life needs and plentiful in harsh radiation and high-speed micrometeors. We contemplated biology adjusted to the vacuum in our episode Void Ecology, but today we're principally interested in how life can be adapted to space settlements we build, or those settlements we build on planets, moons, comets, or asteroids. While the title of today's episode needs little explanation, it comes with the title of both a book and an annual presentation track, which the National Space Society runs at the International Space Development Conference. That track is one of several that go on at the same time at the ISDC each year, and Living in Space is run by my friend Dr. Sherry Bell, the Dean of Psychology at the Kepler Space Institute. More than one episode on this channel has been inspired by those presentations, including Staying Sane in Space from last year, which discussed the 101 ways space can drive you nuts in just a few weeks on board the space station. Our goal is not to repeat that information, since the book and many other presentations cover those topics very well, but rather to look further ahead. Try to imagine what the future would be like if you were an asteroid prospector, for instance, patrolling deep space in a small ship, hoping to find and claim a small rock as your own and mine it. Probably all the easy finds are already mined or claimed, and this means your life in the future is strikingly like it was for your ancestors in the distant past, where a great deal of time was spent searching for and gathering resources. Or an asteroid miner who might be essentially living in their spacesuit all day or even all night, augmented by its powered exoskeleton and advanced electronics. By the time people start wearing spacesuits for an everyday job, we would expect it to be more comfortable than now, and maybe even like overalls or even a second skin. Perhaps you're the bartender at the pub on the station where miners bring back their ore so it can be refined and fired by giant electromagnetic cannons back to Earth orbit. Or maybe jobs like that are automated, or is having a friendly human to talk about your day a job we want a human specifically to do. Perhaps people would be comfortable with a ChatGPT-enabled PubBot 3000 with a wider array of cocktail and conversational options, who can look up all your data and recommend the perfect beverage, selected optimally for your unique tastes and preferences, for you to share and enjoy. Or maybe you're a space farmer waiting for your climate-controlled crops to be ready and for a ship to dock and take them away, as it does every month. And perhaps almost the only visitors your small community, or perhaps just your single family, ever get. The family farm of 2500 AD might tend to 100,000 acres of robotic farms in space, mere seconds from their client communities for conversation or virtual reality, but a few days of travel if you want to gossip face to face. Or perhaps you live the life of a solar array tender who spends the days running inspection and repair robots on the huge thin arrays, and goes EVA every couple of days for an hour to float on a structure no thicker than paper but as large as most cities, and yet populated by you and your 5 crewmates. Space is immense, and its future will run unnumbered trillions of years, and so almost anything we might imagine might occur in it, and that should include a trillion different jobs and billions of different types of facilities, each different than each other, even when made from the same blueprint, and each changing with time. Much of our efforts towards living in space are about trying to make any given bit of it more like Earth, a process we call terraforming, while others will attempt the reverse, namely adapting to the environment. An example of this is bioforming, where you alter people to the environment, an extreme case of which would be giving someone gills to live on an oceanic planet, for instance. We are not contemplating anything so large today, but we must be mindful again of just how huge space is, in time as well as volume, and some colony established on ocean planet near the galactic rim after a series of leapfrog settlements of a dozen prior worlds spread out over 1,000,000 years might be far more divergent from us than what even 1,000,000 years of evolution and cultural change might naturally allow for. Growing up under alien suns and with access to a vast knowledge of genetics and cybernetics might mean our distant children on that world shared less with us of mind and body than any animal that ever walked our world or swam its seas. But again, our focus for today is much closer to home in space and time, and those represent problems enough. To shine a light on those topics, we might as well begin with light itself. It has been almost 150 years since Edison demonstrated his carbon filament light bulb, more than twice as long as it's been since the first humans went to space, and so it is easy to forget how new artificial lighting truly is. Candles and fires were very inefficient and expensive ways to allow enough light to work when the sun went down, so we didn't get much done at night. Electric lighting changed that, the result being we are much more used to artificial lighting than our ancestors. Our modern civilization relies heavily on artificial lighting, and that would seem sufficient proof humans can be comfortable with artificial lighting. But the data coming out these days is indicating that such a relationship might be a lot rockier than we had thought, and that in many cases it behooves us to aim for as close an approximation to sunlight as possible. Inside our own solar system at least, natural light is in the right spectrum, as it's the same sun, except the brutal frequencies of ultraviolet are filtered out by our atmosphere. However, space away from any planet's shadow is a perpetual noontime summer desert light without any evening or sunset. Some asteroid miners making their way out to the belt or combing it for prospects will never see night for months on end, as the sun slowly grows dimmer as they journey out, but never disappears. I don't think I'd sleep well that way in a world with no nights, nor afternoons and evenings, just eternal noon. While we often talk about how light would be brighter or dimmer on another planet, or its day and year shorter or longer, the color temperatures matter a lot too. This can get confusing because before we did much science on light, we had our normal old rainbow of colors, and red, orange, and yellow, flame colors, which came to be called warm colors, and green, blue, and violet, the cool colors. In reality, almost all the particles of light, photons, coming off a normal open flame are in the infrared, and only a handful are visible, mostly in your red and orange colors. If you are wearing something blue by a campfire sometime, you'll notice it seems especially dark, bordering on black, because that fire emits virtually no blue light to reflect off it. Green would be a bit less dark, while violet would be even darker. As we turn that flame up, make it hotter, the amount of green, blue, and violet light will increase, while the portion that is infrared will decrease. If you look at a torch flame, it's blue near the tip where it's hottest. So too, a hot piece of metal in a fire might begin to glow red. As it heats up, it shifts to orange, then yellow, and then it's usually so bright we are flooded with all wavelengths and it seems white. Our sun's peak temperature wavelength is actually bluish-green, but none of us perceive that, as Earth's atmosphere scatters short wavelength photons, hence a blue sky. Unfortunately, we're stuck with that terminology of warm and cool colors, so you will see a bulb listed as 3000 Kelvin and warm, while a 6000 Kelvin bulb, twice as hot and giving off a spectrum like our sun does, is called cool. And let's be honest, those warmer but actually colder temperature lights in the 2000 to 3000 Kelvin range are more relaxing and warming hues. Those are the colors you get more in the evening and morning, and thus it's no real surprise it's relaxing to us. We're only just starting to gather good data on what light works best for people in what circumstances, as LED lights have made it affordable to use basically any spectrum you want. but the evidence is lining up that we are very touchy about color temperature for our environments. Blue light is not relaxing and not conducive to getting sleep. Conveniently, our sun is one of the hotter ones. For all that we call it a yellow dwarf star, it is bigger and hotter than about 95% of the stars in this universe. So what does all this mean for living in space? Well, up in orbit, on some space hotel where you whip around the planet every 90 minutes, enjoying fast sunrises and sunsets at the same rate, you cannot allow anything like a natural day to come in through windows, even UV-shielded windows. Your sleeping quarters need to be absent of any outside light, which is fine since we have found that the best sleep comes from the least light and noise. Trust me, an investment in blackout curtains and a good mattress are good ones. We think of a space hotel as a place to visit for its microgravity environment, but I'm certain it won't take long for them to get rated by how comfy their beds or sleeping cocoons are, and how good a night of sleep the wealthy tourist had. How do we build a space habitat with good lighting without having to produce it entirely artificially? It is tricky and depends a lot on what the other conditions are. For instance, it's impossible in low orbit. Again, that 90-minute day-night cycle is in play. You could possibly use a system of mirrors and lenses to blast light from ahead or behind your orbit to light you during the day when you're behind the Earth, but that seems needlessly complicated in favor of just enclosing the whole environment, except a few observation windows, and lighting it with the best approximation of a normal day's length and light temperatures, even incorporating seasonal variations. I think that's likely to be your solution at most places. But in higher orbits of Earth where a space habitat wouldn't spend much time in Earth's shadow and the orbital periods get longer, you could have your space habitat spinning on its axis parallel to the direction of sunlight. Then you stick whatever filters you want in place to block out light of the desired frequencies and change them over the day and season to mimic a given region of Earth. You can also bounce or direct that excess light into power collectors or power storage, or running something like fuel production or metal refining, or secondary space farms or hydroponics in lower quality, cheaper adjacent facilities. This works essentially anywhere except or in a planet, major or minor, or in low orbit of it. You could even put a big parabolic dish behind your hab to bounce in a larger amount of sunlight if you are far from the sun. It is paper thin or even thinner, so not much of an extra cost even way out in deep space, as we discussed in more detail in our recent look at colonizing the Kuiper Belt. This is going to be a bit of a theme when it comes to planets and living in space, that it tends to be way easier to make the blank template of space into something Earth-like than it is to reshape a planet. You have a blank if hostile canvas to work with, not one already painted Martian red, so to speak. Of all the planets, only Mars has anything close to our day length, being half an hour longer and presumably allowing some extra sleep each day. The other rocky planets have day lengths measured in months, while the gas giants are all shorter, with Jupiter at 10 hours, Saturn 11, Uranus 17, and Neptune 16 hours. Most asteroids spin around even faster than that, and only a handful of tiny moons near Jupiter and Saturn have day lengths of 24 hours or less, with most moons being tidally locked and having days equal to the orbital period around their planet, like our moon, and are often weeks or months long. As we move to a gravity environment, this problem only gets worse. We know microgravity is bad for people in the long term, but we have no idea how little is enough. Only 12 humans have ever existed in low gravity, and only for a few days each in lunar gravity, with that stay bookended by high-G rocket burns and periods of microgravity moving to the moon and back. So for all we know, the moon and the dozen or so other bigger moons in this solar system might be just fine for humans, in which case settling them is far easier, whereas if it isn't, then we may use human repair crews on short month-long contracts and have robots on the ground, or remote control them from spin gravity habitats orbiting those moons. And if gravity is too low on those moons, maybe Mars is fine at about 2/5 Earth's gravity. Or maybe even Venus and Saturn, each within about 10% of Earth's gravity, would still not be close enough. Earth's gravity has been the same over the entire duration of life here, and varies by less than 1% from pole to equator or valley to mountaintop. Nothing is adapted to gravitational variation. We could find that some ecologies totally fall apart even at just under a 1% difference in gravity, so that even the cloud cities and floating gardens of Venus, floating 100 miles over the surface, need constant tinkering to help with gravitational issues of its near-Earth gravity. Perhaps your job there as a botanist or zoologist is helping with that tinkering and adjusting for the gravity not being quite right, and your spouse helps run the local tourist rental for gliders and blimps and acid-proof pressure suits. My hunch is that the gravity on Venus would not be a problem at all, but science is about rigorously testing hunches, and as of right now, we haven't developed the means to test this one. It may be that our tolerance and adaptability, and those of our fellow organisms, is so high and quick that even bizarre environments with just 1% gravity would be able to be adapted to. Places where we're floating in 3D environments and where you glide around like a bird are easy to create and dwell in. Those habitats might sport trees a dozen kilometers tall or wide, with entire glades or pools hidden in the various nooks of their branches, while microgravity trees might grow out spherically. But it is very important to know for our future, because that future looks very different if humans can handle low gravity very easily, or if treatment for microgravity health concerns becomes simple and routine. So too, a civilization with easy cancer treatment might build very different ships, domes, stations, and other settlements than one that dies easily from radiation exposure. Alternatively, we can say that humans experience acceleration from being spun around, like a car going around a sharp turn or laundry in the spin cycle does show every evidence of simulating gravity sufficiently, with a few caveats we'll get to in a moment. First, some do wonder how we know gravity and this sort of use of centrifugal force can approximate each other. And the answer is right there in things like the microgravity in space stations, or any satellite around our planet, or any other moon or planet for that matter. They don't fall down toward the planet because the centrifugal force of them whipping around that object counteracts the falling. That's why astronauts float on the space station, and it's also why you wouldn't float if you jumped up toward the center inside a rotating space habitat. It would seem like you would float off the ground in a spinning cylinder, and indeed you would if you magically appeared inside one by teleportation, at least until all the air started shoving you around. But the same is true if you teleported in over Earth. There will be an instant before gravity affects you, or vice versa since it travels at light speed, and then you would fall under the power of gravity. The real confusion comes from people not really thinking through how you jumped off the surface of that ring or cylinder to get suspended in the air, and not carrying through the inertia or looking at the force chart of jumping off the floor while both you and it are moving. TLDR, if you're content to accept that spin gravity works fine, I have never heard of another physicist objecting to it working this way either, but often folks hear about the idea and it confuses them, or they think the idea is something out of sci-fi or fringe physics when it's terribly mundane and old school. It's just a pain to visualize and requires messing around with rotating non-inertial reference frames, which is also a pain. The other half of that skepticism, I think, comes from the lack of any existing space stations with spinning sections. However, this comes down to three key facts. First, one of the major points of us having a space station is that we can do experiments in space there, and the only thing we can't really emulate down here that is up there is that near absence of gravity, or rather that near perfect balancing of centrifugal force and gravity to create that weightless microgravity environment. We could build a big long tunnel around the planet's equator, suck the air out of it, and run a Hyperloop-style vacuum train around the planet at thousands of miles per hour, and achieve the same thing, but as expensive as space stations are to build, that would be worse. Admittedly, it would have great travel uses. Anyway, putting gravity onto the only place we can conduct zero-gravity experiments is kind of self-defeating. I suspect we will find many folks enjoy microgravity in our early space hotels, but soon find they would like at least partial gravity in their hotel room itself. It certainly makes plumbing easier and less embarrassing. Those people aren't living in space, but maybe the customers are the first people who really do. When it comes to your hotel staff, which is not usually a very high-paying job, it might be that the cost of bringing them up to space and down is so prohibitive that such companies pay extra bonuses to those who stay on longer between trips home to Earth. The second reason is it's more expensive to build since you have either a large cylinder, wide enough for reasonable spin gravity, or you make a ring or torus, and for the latter that means you have even more surface for air to leak out from and radiation to leak through, raising costs. And third, while we could have a station that had a spinning section connected to a non-spinning section, that is a lot harder to do than it sounds, as you have a collar or section trying to mate those two bits up that has to be airtight. It is doable, but it is also a hassle and tends to result in some leakage, which is fine, all stations leak, and needing some power to keep that section spinning. Any strictly rotating space station doesn't require any power to keep it spinning once you get it up there, but I suspect most real space habitats will still have to use some way to handle matching it up to whatever non-rotating structure is attached to them. For instance, it's handy to place a habitation cylinder or hab drum inside a thicker non-rotating sheath, superstructure, or hollowed-out region of an asteroid. Now, I mentioned that spin gravity wasn't a perfect match with normal gravity, and a key part of that is that you have to spin faster and faster the smaller you want to make a habitat, and people get nauseous from rotation. You may be watching this on a swivel chair, and if you're like me and have it at a U-shaped desk, then it is normal to rotate that chair partly around or all the way around a few times a minute, and it would be normal for doing that to cause no nausea, not like the dizziness of just lifting your feet and spinning around in that chair every few seconds and repeatedly. This is the nausea we worry about for spin habitats, and it is quite mundane, but it means that anyone in a ring or habitat that's only a dozen feet wide has to spin around 22 times per minute, or 22 RPM. They would also find that their head, near the center of the spinning cylinder, was experiencing virtually no gravity effect, and indeed if they were over 6 feet tall, or jumped a bit or stepped on a footstool, their head would now be experiencing not just low or no gravity, but instead a small upward tug. Studies have shown that low-radius spinning habitats are intolerable due to Coriolis forces. A maximum rate of rotation of 2 RPM is often specified, although some studies have indicated humans could adapt to 4 RPM. A maximum rotation rate of 2 RPM, producing 1 G, gives a radius of 224 meters. If a rate of 4 RPM is considered acceptable, the radius can be reduced to 56 meters, 184 feet. A rotation rate of 22 RPM is impractical, at least for humans. Spin gravity grows with distance from the center of spin, twice as far away, twice the gravity. This is the opposite of normal gravity, which is inverse square, meaning twice as far away, 1/4 the gravity. So it is actually easier to work with in that regard than normal gravity, but it means your station, while not needing to be anywhere near the size of a planet, does need to be big enough that folks walking around it experience no significant change in gravity between head and feet. And also the first and second floor of a building, although lower gravity at different heights might actually be a popular feature. You could, for example, have an Earth gravity floor, a Mars gravity floor, and a lunar gravity floor, as contemplated in the Gateway space station design some years back. All of this means we tend to be looking at either creating a moderately low gravity environment, like simulating Martian gravity in Earth orbit, or something that is at least 1,467 feet wide or 447 meters to achieve that 2 RPM threshold at normal Earth gravity. Needless to say, that is outside the price tag of what we are ready to pay right now for a space station. We usually assume this is a ring or cylinder of that diameter, but what we call a hammer hab works too, which is where you have your rotating section swinging around on a tether or similar rather than a complete ring. And while we're pretty confident 2 RPM as a rotation rate should be fine for any human, we can't be quite as sure that would be true of other organisms, and the same for gravity variation. Which takes us to the discussion on non-human life, by which I do not mean aliens, at least not in the classic sense. Humans are probably fairly normal examples of how mammals will handle something like an O'Neill cylinder, a big wide hab drum whose full-size version is comparable in living area to your typical US county. At 5 miles or 8 kilometers wide, they only rotate once every 2 minutes, or half an RPM, so not nausea-inducing. Such an environment is big enough to create real ecosystems, not just boxes in space for humans and some short-term experiments. But if you're trying to replicate whole ecosystems, you do have to worry about how fragile your most sensitive critter is. As an example, I really doubt any mobile organism is going to have a problem with spinning around once every other minute. Otherwise, it would have a rough time moving to flee predators or prey on something, which is rather the point of being mobile. Trees might be more sensitive, not being mobile, given that Earth only spins once a day or 0.007 RPM. However, they have to survive winds and gusts, so they are probably not that sensitive. We don't actually know though. On the other hand, we do know that bees navigate using the sun, and it is ultraviolet light. So if you're spinning that hab at 0.5 RPM, not 0.007 RPM, that might really mess with their ability to use it to navigate by. The rest of us might not like having a window that looked out on the starry night and swung completely around every 2 minutes either. Physically spinning around in circles isn't the only way to get motion sickness after all. So you enclose your cylinder and control light coming in or create it entirely artificially, including non-visible frequencies like UV or infrared. That is all doable, but it definitely takes extra effort. And moreover, while that lets you fix the gravity to whatever you like and the lighting in day and year length, unlike any planet you might settle, but the more things you have to get right, and the narrower that range we find ourselves and our fellow Earth organisms can handle, the harder and more expensive this all gets. That brings up that balancing act of terraforming versus adapting yourself to the environment, and with bioforming as an extreme example of that. We might find we're okay with modifying honeybees to work differently, or just use some other pollinator. We already have been breeding bees and other critters to be more docile or productive for thousands of years. Now we just have better technology for that, and likely will be even better at it down the road. The thing is, tinkering with an organism is also tinkering with an ecosystem. Even a small change in one organism can throw everything else out of whack as a result. Think about a forest in which beavers were far more common and productive and predator-resistant. Before long, there was probably a lot less forest. Some things might be easy adaptations of time. We presumably did not evolve living under roofs, but it's normal to us now, and having your blue sky replaced by a green lawn or forest hanging overhead is probably doable. But we have often found that things we would assume we would handle easily were surprisingly rough on us physically or psychologically. We have ways we could fix that, including a fake sky on a small cylinder nested inside the main one, but we also have ways to combine spin gravity and normal gravity to make higher gravity habitats on low gravity planets. We can use solar shades and mirrors to adjust apparent day length, including seasonal variation, or even brute force alter a planet's rotation or mass. We have discussed heavy-handed approaches to terraforming in other episodes, and they're not that far-fetched in a practical sense. All of these habitats or terraforming operations require a lot of effort to accomplish, not to mention cost, but that always needs a caveat of scale. Greater technology and automation allow modern humans to enjoy houses that most kings of yore would call a palace and envied, and that they would immediately attempt to seize for themselves. I don't think most folks used to watching or reading about those cultures in fantasy or history tend to realize how small and cramped your typical castle or great house was, as well as dirty and hot or cold. Better technology and automation allows us to do things easier, and we are not that far away from being able to not just have factories mostly run by robots, but robots that build other robots and which require less attention and control than modern ones. How expensive is it to really terraform a planet if you can dump one vial of bacteria on it, which can grow and reproduce, then come back 1,000 years later and find that planet has got air, soil, and basic organisms on it? Well-engineered machinery that does similar is presumably just as possible and need not be totally independent in reproduction. We can have a robot ecosystem of thousands of different types of robots, big and small, and we can set that up so they are not independently reproducing like our organisms do. The simpler and more repetitive the task, the easier that is to design and oversee construction or maintenance of, and fundamentally a giant rotating habitat is not much different than 1/10 its size. Much as a freeway is huge compared to a carefully carved stone statue, size is not a great indicator about effort and cost, and varies a ton based on technology, especially as a 3D concrete printer or a robot with a chisel arm might make statues very fast and cheap too. So we cannot trust our intuitive sense of what is practical versus ridiculously over the top when thinking about the scale of megastructure construction or terraforming. That's why this show discusses concepts like building Dyson swarms, or englobing black holes, or even making a black hole, because as huge as englobing Dyson swarms are, they are allowed under known science and aren't prohibitively complicated. They are conceptually simple, and they are thought to be physically possible, and that means they are plausible to build and not necessarily in some future of godlike posthumans. Now, it is entirely possible that living in space will come after we have transitioned into some transhuman or posthuman state that no longer needs nor wants terrestrial ecosystems, or one that has been wiped out by AI who similarly do not need those kind of ecosystems, and I would argue both of those are alive and thus would fall into the scope of our episode for today. However, this episode is less interested in physical modifications to humans or what some cyborg, AI, or alien might be doing. So let's talk about the cultural changes that living in space offers. First, one of our strengths and weaknesses as a species is that we are social by nature and required to be by practical life. We have to mostly get along with our neighbors at a day-to-day level and have a lot of customs for managing that, which vary from culture to culture, many of which are influenced by the local environment and technologies, and space would be no different. However, it does present some unique problems and advantages. For instance, just as some planet with a 26-hour day and 2 moons, one orbiting every 8 days and one every 32, is likely to have a culture built around that, folks in artificial habitats can choose to build a culture around the number 10 if they really wanted to, going for a 100-minute hour, 10 per day, 10 days a week, 10 weeks a month, 10 months a year, and so on, which would certainly be easier to learn and work with in our modern timekeeping. This is a similar situation with post-scarcity economies, the kind that have robots and are just ridiculously prosperous by modern standards, because they basically have the resources to make any system work if they are just stubborn about it. Folks debate about which system is more efficient: capitalism, socialism, communism, anarchy, etc. But a post-scarcity civilization can probably get away with picking its leaders and policy by random lots, or using a Ouija board or a bowl of alphabet soup to pick their next king. That's probably not stable in the long term, but then again, nothing really is. And the nature of the sort of civilizations that grow out of massive automation and energy abundance is that they are so huge in scope and possible population that you are almost bound to have semi-functional examples of virtually any crazy system in place at a given time somewhere, and possibly supporting itself in part on tourism from folks who want to see that in action, like some Wild West reenactment village. That's one of the big draws to space for a lot of us. If you can imagine it, this sort of civilization can make it a reality. Admittedly, so can virtual reality, and what's nice about that in a peaceful sense is not that there's more than enough room for everybody in the immensity of space. That's poetic, but it's really our neighbors that set our teeth on edge, not the weird loonies in that other country with that bizarre habit of theirs that we've heard about. VR and the internet let you interact with people all over who share your less common habits. And what's really cool about space habitats is that they are inherently mobile and smaller, so people can individually migrate, and so can whole communities. If 2 O'Neill cylinders in a local swarm can't stand each other, one can undock and move to another swarm. But surely space itself has some cultural changes inherent to it. Well, yes, I think so, especially in the near term. Recycling might be an example. Everything about living in space is about needing to be good at recovering and reusing resources, and even a very post-scarcity civilization is bound by this. In big space habitats, there may be little need to make rooms airtight in homes or personal quarters, or to walk around in a spacesuit. In other places, some sort of pressure suit might be as routine as clothing. It might be comfortable clothing too, as light as a sweater or even a feather, using advanced materials, or maybe heavy and thick but interwoven with servos and electronics and radiating tubes so that you don't just have the machines in your gear carrying their own weight, but possibly intuitively amplifying your own strength and speed. Or maybe the technology never improves as much, and on asteroid colonies, kids learn how to rapidly don their spacesuit helmet in the same way we learn to look both ways to cross the road, or tie our shoes, or know where the fire exits in a building are located. And maybe the built-in recyclers on their bulky suits are so good and practical that they don't take them off much. They use the bathroom in them, the internal systems clean their skin, and remove waste and so on. Maybe they sleep in them. Given that we spend our early years in diapers, this might be an easy adaptation for kids born and raised there, queasy as it sounds to us. Other places might have habitats so idyllic they require no houses, with ceiling or walls for protection from the elements, and no spacesuit or even clothes for the inhabitants. Meanwhile, other places might be so inherently harsh that living in a spacesuit all the time is the only real option besides cybernetic alteration. And of course, many might choose that, or already have it chosen before going to space. Indeed, the term cyborg originates from discussion of adapting people to living in space. In the end, we could tell a million stories about how life might be in space and barely crack the surface of the options of future humanity we'll have to explore. But one thing seems sure, given many options for living here on Earth and how tiny it is compared to space, the future for those living there seems practically limitless. There's 1,000 stories we could delve into about living in space, but one that really spoke to me to delve into more since writing this episode a few months back was life as an asteroid miner, and so we have a Nebula original exploring what it might be like to be out in the belt in the centuries to come, prospecting for minerals, and if we would see lone miners on asteroids or big teams, or something more like the mining camps of the California Gold Rush, and the sorts of suddenly booming communities or ghost towns that sometimes followed, and what that lifestyle and community progression might look like in a space setting. If you want to see that bonus episode, you can subscribe to Nebula, our streaming service, where you not only get to see every regular episode of SFIA a few days early and ad-free, but all our other bonus content, including extended editions of mini episodes, and more Nebula original episodes like Nomadic Miners on the Moon, Space Freighters, Retro Causality, Orc OR and Free Will, Conformal Cyclic Cosmology, Colonizing Binary Stars, and more. Nebula has tons of great content from an ever-growing community of creators. Using my link and discount, it's available now for just over $2.50 a month, less than the price of the drink or snack you might have been enjoying during the episode, and it goes to supporting new content from myself and other creators. When you sign up at my link, go.nebula.tv/IsaacArthur, and use my code IsaacArthur, you not only get access to all the great stuff Nebula offers, you'll also be directly supporting this show. Again, to see SFIA early, ad-free, and with all the exclusive bonus content, go to go.nebula.tv/IsaacArthur. One last quick note, folks often ask if we're doing another lifetime membership drive for Nebula, and for the month of September 2023, you can get a lifetime membership, for as long as both you and Nebula exist, for $300, which goes to developing more and bigger Nebula originals and platform improvement. And if you sign up using my code, IsaacArthur, a third of that goes directly to the channel. So that's it for today, but we're just starting for September. On the 14th, we'll ask about the interplanetary infrastructure we need to build in our solar system to colonize it. And then we'll jump into Sci-Fi Sunday on September 17th to celebrate SFIA's 9th birthday with the Fermi Paradox Fallen Empires. Then on the 21st, we'll talk about how we can mine atmospheres like those on Venus or Titan, or even gas giants and stars. Then we'll close out the month with our live stream Q&A on Sunday, September 24th, and then on the 28th, we'll have an exploration of what traveling the galaxy as an adventurer or lone wanderer will be like in Have Spacesuit, Will Travel. If you'd like to get alerts when those and other episodes come out, make sure to hit the like, subscribe, and notification buttons. You can also support the show on Patreon, and if you want to donate and help in other ways, you can see those options by visiting our website, isaacarthur.net. You can also catch all of SFIA's episodes early and ad-free on our streaming service Nebula, along with hours of bonus content at go.nebula.tv/IsaacArthur. As always, thanks for watching and have a great week.